Hey there, kiddos. We're going to start section 2,
Section 2.2,
2.2 of chapter 2, section 2.
power functions and models.
Power functions are like polynomials, but
not exactly like polynomials. So here's the difference. A polynomial had to have an integer exponent and it could be 0 or greater. With a power function, for one thing, we only have one term here, so it's like kind of like a monomial. Like
a monomial
one
polynomial.
Term. Yeah, only one term. But now our requirement is that our exponent has to be a non-zero constant.
So hold on.
Okay.
Non-zero.
Non-zero.
Negative 2037.
That's non-zero.
Negative 1/5.
That's non-zero.
Okay, pi.
That's non-zero.
Square root of 2.
Non-zero.
Square root of negative 1.
That's imaginary.
Oh!
But so also like 5. 5's non-zero.
Yeah, but everybody knows 5's non-zero.
What's the only thing that's not non-zero?
0?
0. So everything except for things with a 0 for an exponent. So we can have fractions, we can have negatives, we can have positives. You're not going to see this situation, so if that freaked you out to see a pi or square root of 2, we're not going to have those exponents.
But if you wanted to be really cool, you could just write it down.
Yeah, if you want to.
Yeah.
Whatever. So the thing is that we have it set up like this f of x equals k times x to the a, where k and a are non-zero constants, because if k was 0, then this would just be 0.
We know 0 times anything is
0.
Yeah.
Okay. And we call a the power, okay? We're used to that kind of notation. And then k is the constant of variation, or we could call it the constant of proportion. Those words mean the same thing.
But 90% of the time with this particular textbook, it's going to be constant of variation.
Right, they're going to ask you about the constant of variation, and it's just whatever the coefficient is of the x to the a.
Right, and it's almost always a k, but sometimes it's an n. It just depends on where you're looking and the way that the teaching is designed.
Right, so we say f of x varies as the 8th power of x, or f of x is proportional to the 8th power of x. And actually, we talked about this in Algebra 1 or Algebra 2. Like, we discussed the fact that things can vary directly and they can vary indirectly. Okay, and that those are two different things. Also, if all you see is the word varies and nothing else, then that would be a direct variation. So if all you see is varies and no other things to indicate, then it varies directly. The other thing you could see with indirectly is you could see proportional, and that means indirectly. What if we talk about these things down here?
Yeah, let's mention them real quick.
Okay.
So if you look at, say, for example, the circumference of a circle, that's something that you've used probably a minimum of 1,000 times in your life. Well, believe it or not, you were working with a power function. Why was it a power function? Well, it's got a constant. And what is that constant? It's really weird looking. That constant is
2 pi.
2 pi, which, Ms. Stevenson was busy underlining. And that is a constant because everybody knows that 2 is constant. That's probably not the issue. But pi is constant. It never changes ever, not even once.
Right, and so 2 times that never-changing number
is another never-changing number.
Right,
yeah.
So our constant of variation is the 2 pi part of this. So r is our, what do you call it, variable? R is the variable here.
Because that's the thing that could change.
Right, and what's the power?
It's a 1, even though we don't write it. How many r's are there?
There is an r to the first power.
There's an r to the first power.
Okay, so area of a circle.
Same setup. A equals pi r squared. And again, pi is our constant of variation because it's the one thing that never changes. The radius does change. It's the one thing that we can pick. And guess what? It's being squared. And anytime you have something to the second power, you're being squared.
Yeah. So in these first two cases, we would say that this is direct variation.
On both parts.
Or that they vary directly, or maybe just that they vary. Like, this is the situation that's going on. And the thing you need to remember is that these are all on the same level. We didn't put any fractions in.
No division.
No division. So these vary directly. Now, force of gravity. Check out this one.
We got a fraction in there, which means it's not direct anymore. But it also means we need to look in a couple of different places. Like, where is my variable? It's that thing with the exponent on it in the denominator there.
But we don't want to. It's not in the denominator in our form up here.
So how do we get it out of the denominator?
We change the exponent sign. So we move it up to the top.
And when a number changes from the bottom of a fraction to the top of the fraction, the exponent on that number becomes its opposite.
Yes.
So in this case, that positive 2 is in the denominator. We can put it in the numerator by making the d to the negative 2. And that's going to be the exact same phrase as the one in red. Which now, though, lets us see everything. Yeah.
In the constant of variation.
The power is going to be negative 2, and the constant is k. And the reason it's k is that's the one thing that's not changing.
Right. That's they're going to give us, if we had a problem where we were actually trying to do something with this, they'd have to give us enough information for us to be able to find k.
Right.
So that would be a constant based on what the problem is. So this is indirect variation.
Boyle's law also strongly resembles the force of gravity, so it also would be indirect. And just like with the force of gravity, we had to investigate what was going on with d squared. We're going to do the same thing with p. We've got to move it from the denominator to the numerator so we have the same shape. And when you do, that exponent of 1 becomes a negative.
Right, because it's normally a p to the first power on the bottom, but we're moving it to the top, so that's p to negative 1.
Which gives us a power of negative 1 and a constant of variation of k.
Now, let's try this ourselves now. Let's try to set up a formula based on some information. What do you think?
Next slide.
Yeah, on the next slide, of
Sounds
course.
good.
Okay.
Hey there, here we go, writing a power function from a given series of connected words.
Also known as a paragraph. From empirical evidence. Hey, what is empirical evidence?
I have no idea. That's like the Empire State's Building. You know, it's got the like tall thing and deal on the top, and you can jump off the top if you want to.
That's not really what it is.
Okay.
Okay, good. We're writing. Empirical evidence is evidence that you get from doing experiments. I'm pretty sure. So, from empirical evidence and the laws of physics, it has been found that the period of time t for the full swing of a pendulum varies as the square root of the pendulum's length L, provided the swing is small relative to the length of the pendulum. Express the relationship as a power function.
I think we should get Mr. Keister.
I think that we should try not to focus on the physics part of it, because all we're doing is writing a power function, and we already know how to do that.
But it said empirical evidence and laws of physics.
Yeah, it's okay though. Look,
okay.
The period says found the period of time t. So we have t.
Capital T, as it were?
Yes, in this case, t equals, it says it varies, and it doesn't say indirectly or proportional, so that means it varies directly. So we're not going to put a fraction, but we do, because it varies, need to put a constant, like a constant variation, like k.
So anytime we're reading this and it says varies as,
just
it's going to
throw
be
in a k.
Equals k.
Yeah.
Equals k,
Yeah.
and then everything else.
Unless they specify that you should use a different letter for your constant.
Okay, sounds good.
Okay, and then as the square root of the pendulum's length L. So square root of the pendulum's length L. Okay, it's all on the same level, no fraction, because it varied, and it didn't tell us indirectly, which means it varied directly. So right here, this is our answer. That's all we had to do. We didn't have to know anything about physics.
Wow, that's amazing.
It's my favorite type of physics problem.
Yeah, the ones where you don't have to know physics?
Exactly.
I love those problems too.
Yeah.
Okay, so now for the meat to go with the potatoes of the power functions.
Yes, so we need to state the power and constant of variation for the function. We want to graph it and analyze it.
The analyzing is super important for this course in general.
Right. It's something that we do a lot, is we analyze functions. Now, in the problems in your book, it specifies that the way we want to analyze it is similar to what is shown in example 2. So if you're like, where are they getting all of this stuff for us to analyze? Look at example 2, and that's where it's at.
And when you're asked to analyze, when you are asked to analyze,
you
will need to include all of these things.
All of these things.
All of them.
There's 9 of them.
That's a lot of things.
Okay.
So here we go.
State the power and constant of variation. So let's rewrite this as something that looks more like a power function. The cubed root of x is the same as x to what power?
The 1/3 power. I know that one.
Right, and the 3 comes from this little number right here. Because we're not squaring x or anything, x is to the first power. That's why there's a 1 on top. So now this looks like a power function. What's in front of x to the 1/3?
I know exactly what's in front.
Yeah?
Yeah, there's only one of them.
So it's 1x to 1/3. Okay, so let's state the power.
Power is 1/3.
Right.
Constant of variation is 1.
Now I'm going to abbreviate the constant of variation as k, because remember we've been talking
that's
about
what we've been using.
that k is typically the constant of variation, and you said it's 1, right?
There's only one.
There's only 1.
There's only one.
Now we're gonna graph this. So just throw this into your calculator.
Yep, and take a peek. And hey, it's on the screen.
But yeah, right there. Is it gonna?
Yeah, right.
I mean, yeah, it's right
there.
there.
It is. Okay.
Okay, so let's analyze it. And so on example 2, and if we go through, the first thing we need is domain.
So the domain on this guy happens to be all real numbers because there's really nowhere that we can't take a cube root of something.
Right. There's not anything you could plug into x and not get an answer. And if you're looking at the graph, you'll see it continues to go to the left and to the right forever.
And
for the
ever.
whole screen.
It's like it's married forever and ever.
Right. So domain, negative infinity to infinity, all real numbers. Then we want to look at the range. So range is our y values. Now, again, you may be a little skeptical of this, but that graph continues going up and to the right and down and to the left forever. No. So it could get to, in theory, negative infinity.
It'd take a long time.
Right. But if you kept like scrolling over, you could get bigger and bigger numbers.
You'll never run out of y values.
Right. So our range is all real numbers as well. Now let's think about, how about continuity?
Continuity, great question.
Okay. Is it continuous?
Can you draw this graph from left to right without picking up your pencil?
I can.
I can too.
So it's continuous.
Must be.
Continuous is hard to spell. Because they're like U-O-U. Like,
yeah.
Okay.
Yeah.
What's after continuous?
After continuous, let's go with, how about asymptotes?
Okay, so asymptotes, if it's a continuous function, there must not be any asymptotes.
Must not be.
Because we'd have to pick up our pencil for those asymptotes.
You could have a horizontal asymptote.
Oh, right, but there isn't one.
But there isn't one on this guy. Even though you're tempted to say and look at this graph and go, hey, there's an asymptote when y is 3 or negative 3. That's not true.
Because we keep going up, we keep going down.
We can find those values that are larger than that. There are no asymptotes.
How about we find Extrema?
How about Extrema? Do we have any peaks or valleys?
Nope. No
none
Extrema.
that I see.
How about increasing, decreasing, or constant?
You know what? I think it's increasing from negative infinity to positive infinity.
You're absolutely right. It goes up the whole time that we're drawing it. And so we could write this one in 2 ways. You could say increasing from negative infinity to positive infinity, and that would be a correct way of saying that. Or you could say it's increasing on its domain.
Increasing on its domain.
Because its domain is negative infinity to positive infinity.
And it's increasing the whole time.
And it's increasing the whole time. So one of those two situations.
That sounds perfect. Okay, we're gonna take it. Oh, sorry about that. Back out of here.
Okay.
So we're increasing on the domain. Are we decreasing anywhere?
No.
No.
If we're increasing everywhere, we can't be decreasing.
We can't be decreasing.
What else do we need? How about
bounded?
Bounded. It's not bounded because we can get all the way up to positive infinity and negative infinity. Sorry, so
it's not bounded.
Not bounded.
Another way to think about bounding is to think about, hey, is there a ceiling or floor that kind of is a barrier to our graph that we don't ever go through?
And there's not in this case. It just keeps going up, keeps going down, forever and ever. How about symmetry? Symmetry,
very good question. This guy happens to be symmetry with the origin.
Yes, symmetric about the origin.
Yeah, good guess. I love it when I get those guesses right.
It wasn't because you know what you're talking about?
It was totally because I knew what I was talking about. You know how you can tell if you're symmetric about the origin? I bet you don't know.
I am. Go ahead.
If you spin the thing around 180 degrees, it'll be the exact same thing.
What's in your first quadrant should be the same if you rotate it around as what's in the third quadrant.
Yes, exactly the
same.
same.
If you look at the graph, which you are
should
right
be
now.
seeing, yeah, it's right there.
Right there.
Yeah.
Okay. And then I think we just have in behavior left. Let me count 1, 2, 3, 4, 5, 6, 7, 8. Yep,
9.
just in behavior.
In behavior.
Okay.
What is in behavior?
Well, it means as x is going towards infinity, what's happening, and as x is going towards negative infinity, what is happening. And the way we are going to write in behavior for the rest of our lives from this point on is with limits. So
limits are super important in calculus, which is why we're going to try and really stress them a lot this year.
Right, to get you prepared. The limit as x approaches negative infinity of our function. So I'm just going to write f of x, but you could put
x to the 1/3 or a cube root of x.
You could put your function there. But what we're saying is as we're going towards negative infinity, so as we're going to the left, what values are we approaching on our graph?
Positive infinity?
No, we're going towards negative infinity.
Negative infinity.
Because our graph is going down and to the left. So
that's what I meant to say.
Yeah, that's what you meant.
Yeah.
Okay, and now we do x as it approaches positive infinity.
Because that's what the graph shows.
Okay, the positive infinity, you're going to the right, and as you do that...
I've got this one.
Yeah.
Positive infinity.
Positive infinity.
Oh, yeah.
Goes up and to the right. That's our first function that we're analyzing. Let's do another one.
Oh, that was so much fun. How could it get any better?
If we do another one.
Let's do it.
Okay. This also needs to change forms by moving the x squared up. We said we changed the sign when we did that. So that's going to be 1x to the negative 2. Go ahead and graph that. And we've got all kinds of stuff here.
So let's just do this real. Back at it again. Sorry about
power.
that. So the power. I've got the power.
Okay. Then what is it?
Negative 2.
Negative 2. I wonder, am I even still in the webcam shot?
I bet you are.
Okay.
Okay.
K, our constant of variation, is?
1, because how many of them x to the negative 2's you got there?
I only have 1.
Yeah, 1 it is.
Yeah, so now we have all these things that we need to do.
All of
the analyzation again. So domain, but this time it's a little more interesting.
Quite a bit more interesting, actually, because what one value can you never, ever, ever, never, ever, ever double stamp-cs have in the denominator?
A 0.
Yeah, because then, life just goes.
You can't divide by 0, and you know why? Because
cats and dogs will start living together. Sheep and lions.
Well, here,
biblical
let's say,
apocalypse.
Let's see. Let's say that we did 5 divided by 0. We're saying take 5 people and put them into 0 groups.
That's easy.
No, you can't do that.
What?
You can't take 5 people and put them in no groups.
So it is it's up like an apocalypse. If we
exactly.
Can do this. Okay,
we're basically causing 5 people to not exist, and that's not okay.
That sounds horrid.
Yeah. So.
All right. So the domain then would go from negative infinity to, but not including 0.
Right, because we're saying we cannot have 0.
And it would go from 0 to infinity because we can't include 0.
Right. Yeah. Right. So basically, we're excluding 0. So we do this fanciness with interval notation.
And if you put a bracket around the 0, that's telling anybody who looks at your paper that you're including 0.
But we just said we can't divide by 0.
Can't divide by 0.
So that's not the case.
No deal.
Also, I kind of screwed up on this parentheses here. Make sure you distinguish, like if you accidentally wrote a bracket, and then let's say you want to change it to a parentheses.
Okay.
Like, what is that? Is that a bracket? Is that a parentheses?
Sideways smiley face.
Yeah, so please erase. Here, let me be an example. Please erase when you mess up. Just get rid of it and then start again. Here, I'll make this. I noticed that issue on the last test.
Yeah, because is it or isn't it? I don't know.
And it's very important. Like, it's not the same thing. All right, let's move on.
Range then, the range on this graph is all the y values, and as you're noticing with this particular graph, hey, all the y values are positive.
Right, because if I take any number and I square it, that makes it positive.
Yeah, it doesn't matter what number you pick.
So what's going to happen is we're going to end up with, can we have 0?
Again, I don't think you can include 0.
Right.
Because you're really close to, but not quite touching.
Yep, you get closer and closer and closer. Now that means that we have, what, if it doesn't ever... Where do we want to go?
Well, let's go to continuous.
Okay,
then.
continuous.
I mean, we'll just keep the same order here.
Is it continuous?
It is not continuous. Why? We've got that domain issue at 0. And anytime you have a domain issue, continuity is not happening.
It's not possible. So we have a discontinuity, and let's say where it's at. It's at a certain x value.
I know.
What?
0 when x equals 0.
Right. There is a discontinuity at x equals 0. So that's an appropriate way of writing that it is discontinuous, but specifically where it's discontinuous.
Okay.
Right?
At 0, yes.
All right, so next, asymptotes.
Asymptotes, there are a couple.
A couple.
There are a couple.
Okay, so vertically.
Vertically, x equals 0. That's where our domain issue is.
Okay, and then how about horizontal asymptote?
Horizontal asymptote will also, in this case, be 0.
Right, because it can't ever get below that.
Can't ever get below that.
0.
And again, your range helps you determine that one.
Right, because that's what stopped our range.
That's what stopped it.
How about extrema?
There is actually no extrema, although if you look at this guy, you may be tempted to say on the little curvy parts in there that there's an extrema, but
there's not. You have to actually have.
You gotta have the bump
or a valley.
Yeah, gotta have the whole bump.
You can't go halvesies.
Can't be some kind of cool curve.
No.
It's got to be top or bottom.
Increasing, decreasing, or constant.
It is. You know what? It's increasing
for a little bit.
Yes. Specifically from negative infinity to 0, but not including 0.
Right, because nothing happens at 0
Nothing.
on this graph.
There's
so
nothing
we would
at
never
0.
want to put a bracket around 0. So increasing from negative infinity to 0.
That's okay. And then it decreases from 0 to infinity.
Right, the other half of the... I don't know why I wrote D, decreasing. Okay, I mean D stands for decreasing.
D stands for decreasing,
But we
Same
need
reasons.
to distinguish from domain. So decreasing 0
And
to
all of
infinity.
these, when you're talking about increasing and decreasing behavior, you're talking about what your y values are doing.
Right.
And
you
then
list your x values.
You list the x
from
values.
From the x to the x, but you're talking about your y values
What the y
going
values,
up,
yes.
or your y values going down.
You got it.
Okay.
Are we bounded?
I think we are bounded below.
I agree 100% with you. There is a floor that our graph simply doesn't go through.
Right.
Bounded floor or bounded
below.
below. So here's a chance to model some quick
erasing
action.
Bounded below. What did I just...
I picked there you go. Bounded below.
Okay. Symmetry.
We have symmetry with the y-axis.
That's y-axis symmetry, because you could fold it on the y-axis and it'd be the same on each side.
You know, like folding wax and smashing down or whatever. Did you ever do that with wax paper? Just me?
I'm trying to spell.
Sorry.
It's okay.
Y-axis symmetry. And then lastly, but not leastly, in behavior.
Right.
Very important that we understand how this works and what the limit rules mean.
Right. So in behavior, as x
approaches infinity.
Yes, the limit.
The limit.
That's what LIM stands for, by the way, is limit.
In other words, the limit is that whole game you played with your siblings in the car on long car trips, you know? How close can you get to them without touching them, but still make them go crazy?
Like the whole, I'm not touching you,
yes,
I'm not
that
touching
one.
you,
I'm not touching you.
Okay.
I'm not, yeah,
Okay.
that one.
Yeah.
And when your parents are like, stop touching each other. And you're like, I'm not touching them.
Yeah.
That's the limit.
So as we go to negative infinity on our function, we're getting closer and closer to a y value of 0. It doesn't matter that we'll never get there. We're saying as we go towards negative infinity, what are we going to get closer to?
Right.
So that's the limit part of that. All right, how about x approaching positive infinity?
Same thing,
Same
it turns out. And you can look at your graph and tell what does it look like the graph is going to touch, and it looks like it's going to touch 0.
It does. It looks like it's going to touch it. It never does, but it looks like it.
Yeah.
Okay. Thing to say.
Why would you start the video that way? So we're looking at power functions and models.
Again, I mean, continuing.
Still looking at them. And we're going to just give you some kind of basic things to think about whenever you're graphing them, because they follow a few simple rules, honestly.
Yep, these rules right here. A few of them. That's a few simple.
Just a few simple rules. So all graphs will that have this power function shape go through the point 1k.
So whatever k is.
Constant of variation, or your...
So like 2x squared, that would be a power function where k is 2, so it would go through the point 1, 2.
Right.
Okay.
The other thing is those with positive exponents will pass through the point 0, 0. So
positive 0, 0. Okay,
yep.
So positive will be passed through 0, 0. Okay.
Negative exponents will have asymptotes with both x and y axis. So yeah, so if you've got one of them negative
like x to the
things,
negative fifth, for example.
that would be yes.
Which, you know, they might write as 1 over x to the fifth.
They might. That one is not the prettiest of ones.
Yeah.
Okay. When k, your constant, is greater than 0, the graph will be totally first quadrant because everything's positive.
Okay. Okay.
Totes.
Everything will be in the first quadrant.
Totes firsties.
Okay.
And if k is negative, then everything will be in the fourth quadrant. So it's...
Is that really true?
Totes fourthies.
So like are we saying that y equals 2x squared lies only in the first quadrant?
Y equals 2x squared for this particular setup.
Because it says x is greater than or equal to 0. So it's just wanting us to look at the right half of the graph, and we all know this is a parabola with a vertical stretch of 2. And if we're just looking over in as x is greater than or equal to 0, then yeah, we would graph this away. So yeah, that is only in the first quadrant. Okay, I believe you. You've made me a believer. So then if k is less than 0, so that's like negative 2x squared. where we're flipping this down. So I'll just graph it on the same little quadrant, like that'd be this
Hey, that's
part.
going to be totes fourthies.
Yeah, that's in the fourth quadrant.
Fourth
Remember,
quadrant.
we label the quadrants 1, 2, 3, and 4. The reason we label them like that has to do with trig. Spoiler alert. So yeah, first, fourth, go. Good to go.
Those came from trig?
Yeah, I would assume so.
I didn't know that.
Well, okay, there's a connection to trig.
Okay, that
right?
I can go with,
Because
yes.
in trig you start 0 degrees or 0 radians over here, and then we go in a circle this way. So I just assumed that, always assumed there was a connection there.
You're probably right.
Yeah.
There's a lot of connections in that.
There is.
Excellent. State values. So we're going to do what we did on the previous slide here. We kind of talked about all the different shapes of these graphs, and now we're going to do it.
Okay, so state the values of the constants k and a. So
2 and -3 for
Right.
that first one.
K is our thing that's in front of our x, and a is our power.
Right.
So it's
-3. Yep.
Now, describe the portion of the curve that lies in quadrant 1 or quadrant 4. Well, that has to do with the previous slide where we talked about those properties. And so let's see, if k is positive, then the graph lies in quadrant 1.
Hey, K's positive. Graph is going to be in quadrant 1.
Okay, so we know it's going to be in quadrant 1, and it wants us to describe the portion of the curve that lies in quadrant 1.
Well, now we need to know about A, because that'll really help us figure that out.
Okay, a is a negative, and those with negative exponents have asymptotes with both the x and the y axis.
I have a great idea,
Okay,
quite possibly, what this is going to resemble.
okay. Should we draw?
It's going to resemble. Oh, yeah. I
Yeah.
just drew it.
Yeah.
Totally first quadrant. Let's rough it out. Rough it out.
Okay, so like if I just care about the first quadrant.
Yes, first quadrant only.
If I have an asymptote that is right here on the x-axis
And
right here on the y-axis.
Yes.
And it gets closer and closer to those without ever touching them, then I've got this kind of a situation.
Hey, that was exactly what I was going to draw.
Yeah. Yep. Yes, it was. Okay.
That's amazing.
So, determine whether f is even, odd, or undefined for x is less than 0. So if we're plugging in negative numbers now, then is it even, odd, or undefined? So basically we need to kind of extend this graph, which I should have drawn it over some. We need to figure out what's going on over here where it's less than 0.
I think it'll be more of the same.
It should be, except it should be down here in the
third quadrant.
bottom right.
Can we draw a mini? Draw a mini. Yeah, there we go.
There we go.
Just barely got it in there.
Okay, and so basically with these types of functions where this is really like 2 over x cubed, right?
Yeah.
With any of those types of functions, if we draw up here in the top right, if it's in the first quadrant, it will also be in the third quadrant because of the fact that it, is a reciprocal graph kind of situation.
Right, and a negative, and that 3 cubes, so like that negative value in becomes a negative value out on the cube.
Yeah. If I were to, like the other way we've talked about even and odd is if I plug in a negative x, what happens? So if I plug in a negative x, hey, guess what? That makes what I had before
completely 100% opposite of what you started with, which makes it an odd function.
Yeah, odd. It is definitely odd. And so these choices are either it's even, it's odd, or it could be undefined.
It might be. It could be.
You might have read that incorrectly at first. I know I did. But either it's even, the function itself is even, it's odd, or it could be undefined over on the left side.
Yes.
Depending on what it is.
Right.
Describe the rest of the curve, if any. Graph the function to see whether it matches the description.
You know what? I think we did that and we described it, so I think we're okay.
Yeah. So, I mean, you'd be better off having a graph of the whole thing.
A little bit bigger graph.
Yeah, that would have been nice, but
yeah.
Oh well. So
that's what they're wanting us to do. Next up is negative 0.4 x to the 1.5 power. Youch.
Okay, so let's just start off right off the bat.
K is negative 0.4.
K is negative 0.4. And A?
1.5.
1.5.
Oh yeah, I'm all over those.
Okay, now describe the portion of the curve that lies in quadrant 1 or quadrant 4.
To the previous slide we go.
Well, K is negative, which means the graph lies in quadrant 4.
Quadrant 4.
And A is positive, which means that the graph passes through 0, 0.
No.
So should we talk perhaps about, like, what does 1.5 even mean as an exponent?
Yeah, we should probably bring that up real quick. 1.5 is actually 3/2.
Right.
And, you know, we're going to talk about this a lot later. And I mean, quite a significant amount at some point in time. We're going to really dig into it. But it's power over root. So if we have x to the 3/2 power, the power part is the 3, the root is 2.
So we're saying this is the square root of x cubed.
That is 100% exactly what I'm saying.
Okay. So that's weird.
That is weird. But you know what what I learned from that right off the bat?
What?
We're not going to have anything to the left of the y-axis.
Which is something they're going to ask us here in a second. But
shoot.
no matter what, if I plug in a negative here, I cube it and it's still negative, and then I try to square root it, but that's imaginary. So you're absolutely right. That is what's going to happen. So first let's talk about, okay, we said it'd be in the 4th quadrant. It has to pass through 0, 0. Okay, and so it's basically going to look kind of like a square root function, I would say, wouldn't you?
Yeah, probably going to look like square rootish.
Maybe you should go and graph this one so we can make sure that
let me just double check.
Because it does ask us to graph the function to see whether it matches the description. Incidentally, the book likes to do this thing where it says support graphically. What that's asking you to do is graph it on your calculator, check to see if you did it right. If not, you need to go back and figure out what you did wrong. It also likes to call your graphing calculator a grapher. That's ridiculous.
Little different shape.
A little bit different shape.
Just a slight skosh different. And the reason we're not showing you the graphs for this particular problem is because we're asking you to find them, which is what we're doing as well.
Right.
And hey, we checked it on our calculator and
realized we had a little incident there.
A little whoopsie, but that's okay. Nothing we can't recover from.
We learned. Now we know what's going on there. So the portion of the curve that lies in quadrant 1 or quadrant 4. So we got that, and then determine whether f is even, odd, or undefined. And we already said that, hey, it's undefined for those negative values.
Yep. Can't do it if can't do it.
Yeah, and since it's undefined for those values, this is the whole graph right
That's
here.
The whole thing.
That's it.
That's it.
Last, negative x to the 4th.
Negative x to the 0.4, I believe. 0.4.
Is it really?
That is really a 0.4.
I can't tell.
Well,
okay.
It's hard to see, but that's what it is.
So k would be?
Negative 1.
Okay, and then a would be?
0.4.
Okay, and what is 0.4 if we wanted to change it to a fraction?
If we wanted to look at that as a fraction, it would be 2/5, I believe.
Right, because it's 4/10 and
4/10.
then you simplify.
Yep.
All right, so...
now, quick recap. We're talking about x to the squared, x squared.
Right.
5th rooted.
So,
fifth rooted x squared. Can I take a 5th root of anything? Yes.
Of
yes,
something.
I can.
Yes, of anything. Any number you get, yes, you can take a 5th root
I can
of it.
5th root a negative.
Any odd root is fine.
Yes.
Yeah. So
100% fine.
You're spoiling it, but we're not going to be undefined for x is less than 0. You know, I think I figured out on this previous one, like how I was trying to think while we were doing this. How would I know that from 3/2 this looks more like a parabola than a square root?
Because
if the number on top is bigger, then it's going to look kind of like a parabola.
Right.
But here, the number on top is not bigger, so this is good. This should look more like a square root.
More square rootish. I agree.
Okay.
I'll double check while you're explaining.
So k is negative, which means it lies in the 4th quadrant, and a is positive, so it passes through 0, 0. So we draw our x and our y, and it's going to pass through 0, 0. It's going to pass through 0, 0. It's in quadrant 4. I said it was going to look like a square root.
So go big or go home. Hey, quick check on our answer.
Okay.
And yes,
okay,
Mrs. Stevenson did not look first.
I didn't look before. It was tempting. Okay, this is the basic idea of what our graph looks like. And then it asks us to determine whether f is even, odd, or undefined. We already talked about it's not undefined because we're allowed to plug anything in. Another thing, if I plug in negatives here, they get squared away.
Oh, and they become positive.
They become positive. So even if it was an even power, it wouldn't be an issue. But we have to decide, is this an even or an odd function? So let's plug in a negative x, shall we? What do you think?
Okay.
Okay.
All right.
What happens if I plug in a negative x?
You get a positive x out.
We get a positive.
You just said that.
I just said that. Why did I repeat myself?
I don't know. Why did you repeat yourself?
Hush. Okay, so we get the same thing we started with. That means this is even.
It's even.
If it's even, I know that it's symmetric about the y-axis. So what I have drawn
there
on
it
the right
goes. Look
side,
there. Bam.
draw on the left side.
That's really good.
Thank you.
Yeah.
I like the left side better than the right side.
I agree, but that's really good anyway.
Thank you.
You're welcome.
Okay, so there we go. That's it.
Hey.
That's, ta-da.
Finished.
Okay.
Dunsies. Okay, so here we go. We're going to power regression on your calculator. And
Fun stuff.
Fun stuff indeed. So you're actually going to see me looking down as I punch it in on my calculator. There will be also a calculator on your screen to help you with this.
Okay, so when you're doing this, only focus on the calculator that you need to pay attention to. Don't focus on the other one.
That's right. There will be two choices.
Also, the Inspire has like the screen, and then it also has the keypad. Take a moment every now and then and pause and say and try to keep up with the steps. If you work through it with us, like you should be able to see which buttons he's pressing as he's pressing them. So if you take it slow while he's working that out, you should be able to keep up.
Right.
Right. Okay. So we want to use the info from the table to obtain a power function model for orbital period as a function of average distance from the sun. That sounds hard, but all you're doing is putting it in the calculator. So,
what am I putting into the calculator?
Huh?
What am I putting in? Orbital distance for x and period for y?
I would think so.
That's what I think.
Okay. So yeah, this is going to be our x's, and these are going to be our y's. Now on the 84, you start off by going to stat and then edit, and you put these into a list, and that's what should be going on. On the Inspire, you have to
go to list and spreadsheet.
You have to create a new spreadsheet and insert this in, and you have to put in an X at the top and a Y at the top on the Inspire.
And you can see all of that happening.
Yeah, it's happening, but that's how you do it as well. So, and then you just have to type in. So.
Give me 1 second, I'm almost done.
Once you have it typed in, you go to stat and calculate for the 84, stat, calculate, and then we want a power regression.
Yeah. There's actually one called a power regression. It's right there.
Yeah, so you want to make sure that your X list is A.
Well, you can even be X on the Inspire.
Okay.
You can call them X and Y.
For the 84, you shouldn't have an issue.
Shouldn't be an issue at all.
It should be fine. And it should pull up and it should show you, what does it show us?
It shows it gives you all the columns, and then
it says it's A times X to the B.
Right, and A in this case is going to be 0.20008.
How many zeros? 3 zeros.
3 zeros.
Okay.
B is 1.49962. And then if you'll notice, it gives you a couple of R values, an R squared value and an R value. All those tell you is exactly how close you are to a perfect fit.
Right, and R squared is the one that would be more accurate.
Yes.
And so that R squared valued is almost 1, like it's super close to 1, which means this is a really, really strong representation of this data.
Right, very strong. And so then once you have your equation, which we've got right here, it says use the model to predict the orbital period for Neptune. Hey, what's the orbital period for Neptune? Well, 4497 gumes.
I think those are gigameters.
Gigameters.
I'm pretty sure I looked that up
from
last
the
year.
sun.
Because,
so,
G like
yo G.
Yeah, gangster, thug life. But not really. Can I say that?
Yes.
Okay.
Okay. So
are we plugging that in for X?
Plugging that in for X.
Okay.
And it's going to have the exponent of 1.49962.
Now, you may be like, are you serious? We have to write down all those decimals, but this is going to give us a much more accurate value than if we had rounded like 1.4, 1.5. That's ridiculous. That's not going to look the same.
Typically, for most of the things that we do in this course, you will want to round off at 3 decimal places. This is probably one of the few instances where the more decimal places we carry, the better off we are.
How about on the answer? Do we want to go with 3?
Yeah, let's go with 3 on the old
so
answer.
0, 5, 1.
2. Yeah. 051. 051. Yes. 051.
And the period of the orbit, which is what we were finding, is this in
This is days.
days?
Yeah, days.
Yeah, that's a lot of days.
So this problem starting off looks really painful.
But it wasn't so bad.
Wasn't so
you
bad
just
at
had
all.
to do power regression in your calculator.
And that's it.
You also